Okay, so what I have here, and this is where I might need to do this for you guys so you can all see at home. What I have is a wooden block, and the wooden block has 2 pins sitting in it. And you can see the 2 pins right there. And I duct taped it to the table just so it wouldn't move. And then the other thing that I have is this piece of string is tethered around the 2 pins. Okay, so that's just the basic setup. Okay, so this demonstration is all about modeling the paths that objects take when they're doing their orbiting. And so I want you to just recognize those couple of things about the setup. I have a string, it's tethered around the 2 strings, the two nails, okay? And so what I'm gonna be doing is simply taking a marker, I'm gonna take one at a time, and I'm gonna be tracing out the path that this would make, okay? So I'm gonna hold the string taut, I'm gonna be as precise as I can, and I'm simply going to be tracing out the path that this would make as I swing around, guiding myself using this. Okay. Here we go. Here's the first one. So I'm keeping the string kind of taut or slightly tight, but not too much because I don't want to pull the block off of its path. I'm going to keep my pen as upright as possible, and I'm just going to swing myself right around. Now, if you're really watching what's happening with the string, you should be noticing, even though I'm kind of half in the way here, and it's not an overhead shot, that the string really is changing in terms of the overall shape that the string is making as I move my way around. And one thing to note, and this is just an accuracy piece, is this spot right here where I started going in that direction. One way that I know that I'm being pretty precise with my hand motions is that I ended in the exact same spot. You know, it might be off like a millimeter, but it's not like I started and when I came back, the 2 lines were really off from each other. So I'm just quality controlling myself, if you will. All right, now the next thing that I'm gonna do is I'm gonna tie another knot, and what I'm gonna end up drawing is a ring, but it's smaller than the next. Now, as I do this, you should start to get the impression that this looks like orbital paths, if you will. If you've ever seen the Bohr model of the atom that Niels Bohr came up with in, I think it was 1912 or something, he called his model of the atom the planetary model because he envisioned the electrons as they went around the nucleus, much like a planet would follow an orbit around a star. So he called his model the planetary model based on what he thought the electrons were doing. Okay, so I'm going to do that again. I'm going to now draw, mark an even smaller knot and then draw that out as well. I'm going to have to just do some quality control here to make sure that my knot isn't too small. Okay. All right, so I'm just going to do it again, different color, just so we can see the differences. All right, so you can tell I'm trying to really do the same thing. I'm being steady and cautious. I'm trying to hold the marker upright. I'm keeping the string relatively equally taut as much as I can. And I'm bringing myself right back around to where I started. Okay, now, if you were to take a look at this from the overhead, where it gets a little tricky with me trying to hold this. Okay, so if I said to you, I'm starting to talk about orbits and planetary paths, you probably, I hope, would agree with me. Like, we're starting to see something that looks like these rings that we've seen in a lot of these images that you guys searched when we started doing this research for the universe structure, pretty similar to what you might see. So one of the things that I would say is important to question is, what shape did I just draw? Okay, so I want you to really think about that. If you were to say one word that represents the shape I just drew, what one word comes to mind?
Circle.
A circle. Okay, anybody else want to vouch for that? Does it look like a circle to anybody else? Rings, right? A lot of times we might call them rings if we're talking about planets, or the things that are around like Saturn, the rings of Saturn. So I would say that that is definitely a word that applies. If I asked you to prove to me whether or not this was a circle, could you do it? So if you say it's a circle and I say prove it, how would you prove it?
There's no necessary.
Because this is science, and the fact is you can't just make a claim that's not validated. Okay.
It's because
so,
it's not.
Even
not,
though this sounds like a relatively simple
end.
claim that we're making, you cannot tell me that it's a circle without evidence to validate that it's a circle.
It's a circle
Now,
because
I want you to also remember that we are taking a piece of string that gets tethered around 2 points. Okay. So what is one of the defining features of a circle? Everybody knows this. Okay. If this was the center of the circle, this finger right here, and I went and drew a line that went all the way around, does my radius ever change in a circle? Absolutely not. Okay. The radius never changes in a circle because there's one central fixed point about which I'm trying to draw that shape, right? Okay. Well, what happens if I now have 2 focal points? How could I possibly form a circle when the overall length of my string keeps changing? So now we have a little bit of a predicament. It looks like a circle, but how am I going to prove to you that it's not? Because it's actually impossible for this shape that I've drawn, it's impossible for any of them to be circles. And I know that because I was not drawing my rings by orbiting around 1 pin. I was drawing my rings by orbiting around 2. So what we need to say is, okay, let me prove it to you. If this is a circle, what should any 2 dimensions be in relation to each other? If it's a circle, what should any 2 dimensions be in relation to each other? It's completely equal, right? Because radius, central point, swinging around. Okay, well, if I sit here and I tell you what these 2 measurements are, and they are equal, then you may sit here and claim that it's a circle. Okay, so I'm taking the first measurement. I'm in this inner white ring. I'm going straight across the middle of the block, and it is 53.0 centimeters in this direction. Okay, now remember that when I'm drawing this ring, this is where the string would be tethered around the 2 nails, but have a lot of room compared to this dimension. Okay, now, again, if it's a circle, this should also measure 53.0 centimeters. It is 50.5 centimeters. That's a 3 centimeter difference. Now you might be saying that's human error. You're a human, you drew the rings, you're not steady enough. Okay, good point. So why don't I just measure the other 2? And I'm going to measure the pink one across the middle. I am at 67.9. It's actually like 67.85, but. And then if I do this dimension, okay, so here's the block. I just measured this way across and it's 67.9. Do you propose that this measurement is going to be shorter or longer than that? What do you think, Sabrina? Is this going to be shorter or longer than this one? It's going to be shorter, okay? And this is because the way the string is getting pulled around those 2 points, but let's just prove it. And this one is 66.3 centimeters. And the thing is too, I know that I'm the one doing this. If anybody doesn't believe me, you can come and measure it yourself. I consider myself to be a pretty accurate measurer. Okay, so now I'm on the green. This is the first ring that we drew. And this one all the way across is 86.5 centimeters. And likewise, you should now already be predicting that if I measure this way, it's going to be shorter. No, I can't be horribly precise here because I can't see that edge, but this one is measuring at 85.5 centimeters. Okay, so the green ring has about a centimeter difference between what I would consider the long axis and the short axis. The pink one has about 1.5 centimeters difference between the long axis and the short axis. And the white one has 2.5 centimeters difference between the long axis and the short axis. So what do we call this shape? Because it's not a circle. It's an oval, okay? And this should be pretty easy to really make sense of now in your mind. I did not take this string and orbit. I'm using that word orbit on purpose because this is a planetary model. I didn't orbit around one focal point or one central location. I was orbiting around two. The length of my string is being adjusted and manipulated as we do that. So here you can see I've got a big triangle, and here I've got like a skewed triangle, and here I've essentially got a straight line. And as we swing back the other way, the string shortens and then lengthens again, and then shortens and then lengthens again. So what does this have to do with planetary motion and orbits? Well, for starters, there are, one of my dots got erased here. These two pins are our two focal points. Now, we all know what the planet is orbiting around, don't we? It's not orbiting around the moon. What's it orbiting around? Big, shiny, yellow, giver of life. The sun. I know you guys are not mute, and I know that you're so smart, so let's chime in. We're orbiting around the sun, but the thing is, if we say that the sun is one of these focal points, then what the heck is at the other one? And this is where people get lost. One of these focal points represents the sun, which is why everything is orbiting around the sun. It's the most massive thing that we have. This is nothing. This right here is absolutely nothing. This is a mathematical point in space, and that tends to drive people bonkers trying to make sense of what's at this point. Okay, so in our solar system, we have the sun as the main focal point about which planets are orbiting. There has to be a second focal point out there in space that serves the purpose of being a mathematical point in space. Okay, now how do we know this? Go back several hundred years to when Johannes Kepler was doing his studies. So 1600s era, okay? And he is looking at stuff in space for weeks, years, like a long time. We're talking 25 years worth of this guy's life was just looking at stuff in space, trying to make sense of it and trying to get his foot in the door working with other scientists that were looking at the same ideas. So what Kepler was tasked with doing was making sense of some of the planetary motions. So it was this guy Kepler, the laws are named after him, plus some other scientists, and what they were observing was this. At times, in the motion of a planet, as they observed, I'm just going to draw a big green dot right on this first orbit because I feel like it. What people were observing, again, this is 1600s, like limited technology, 2 pieces of glass in a tube, looking at stuff, making observations. This is data. What they noticed is that planets seemed to move faster or slower in their orbit depending on where they were. There were times of the year where the planet moved a lot faster. Lo and behold, those times of year are where the planet was closer to the sun. And then if the planet were farther from the sun in its orbit, lo and behold, it moved slower. It's almost like the planets are getting whipped around the sun when they get closer to it, they whip around. Well, guess what? If they didn't do that, then something would probably go wrong with the orbit, and maybe the planet would either get kicked off into space or crash into the sun. So I want you guys to note a couple of interesting things. One is that, and most importantly, and this is where the laws really stem from, is that observations led scientists to noting that these shapes are not perfectly circular. If they were perfectly circular, then scientists would have observed that a planet has an incredibly repeated pattern of motion where it always maintains the same distance from the sun and the same speed. What we observe is the opposite, that the distance and the speed or rate of motion of a planet in orbit changes. Closer to the sun, faster. Farther from the sun, slower. Faster to the sun, closer. Farther from the sun, slower. Did I say that backwards? I might have. Point is that there are 3 main laws that we're going to talk about. And this simple model is probably one of the easiest things to remember in the back of your brain when you're trying to make sense of the laws. They can get very complex, but we're going to actually keep them relatively simple. And really all they're saying is that the paths that planets take are not circular. They're oval, or a more precise word is elliptical. So they're ellipses. And because they're ellipses, then sometimes the distance and the speed of the planet from the sun change throughout the course of the planet's orbit around the sun. So this is kind of this first moment of time to really start thinking about these orbital paths. And I have recorded this session, so this will get posted if anyone wants to come back to it or kind of rehash it. But all in all, this is the beginning of the thinking for the 3 laws of planetary motion. You will also have lots of videos posted from other sources on Classroom that will hopefully get to go through together in class, but they're going to be posted for you. We're going to work together this week to look at some actual notes. We'll take some quick notes on this. And there's some simulation stuff that we're going to do using a cool simulation that I found online. So when we're talking through this week of time, in your mind, go back to this, okay? These are not circular paths because I'm tethered around these 2 focal points. One of those focal points is the sun. In an ellipse, you have to have 2 focal points, and I hate to say it, but there's nothing at the other one. It's a point in space. And because of this, we end up with the change in speed and distance of a planet from the sun as it's in orbit. So I'm going to leave you guys with that, and we're going to stop the class for the day. The other thing that I would just like to remind you of is that those videos I just spoke of are all already posted on Classroom. And this one that I've just recorded, I will get up there as quickly as I can for you guys. Okay, so if you have questions at any point, then that's where you guys email me. Otherwise, I hope this sits with you guys a little bit.